Hello friends and welcome at my channel. Today I would like to start with a new topic. We would like to discuss periodic functions, and I would like to compute how to figure out whether the function is periodic and what is the length of the period. Right, so let's start with maybe f of x being equal to, let's say, 5 times sine of, well, let's say 4x. All right, so the normal sine of x has a period of 2 pi. If we have 4 at the argument, that means that things are happening way faster, 4 times as fast as normal, which means the period of this function is not 2 pi, but 2 pi divided by 4, which is just pi divided by 2. Simple as that. So if we have a periodic function, change an argument slightly, the function is still periodic. That's it. Nothing more is happening. But things can get more interesting if we consider, for example, f of x being equal to, let's say, cosine squared of x. Well, the cosine of x is periodic, but cosine squared seems to be slightly different, right? Is it true? Well, let's see. If you just learn it at school or at the university, you just say, well, no way, I haven't seen that previously. But if you've done some trigonometry, you know, for example, that cosine of squared of alpha minus sine squared of alpha. Well, first of all, you know, if you have plus, it's 1. It's a so-called trigonometrical Pythagoras. But if you have cosine squared of alpha minus sine squared of alpha, this is cosine of 2 alpha. That leads to argument that you see cosine squared of alpha itself, it's sine squared of alpha plus cosine of 2 alpha, and sine squared is 1 minus cosine squared. So cosine squared of alpha equals 2. Instead of sine squared, we're just writing 1 minus cosine squared of alpha, and then we still have plus cosine of 2 alpha. And now we're bringing cosine squared to the left-hand side, so we're having 2 cosine squared alpha equal to 1 plus cosine of 2 alpha, and now we just divide it by 2. So you see, we can substitute cosine squared of alpha through a half plus a half cosine of 2 alpha. Well, we do not care about a half here and a half there, but we do care about the cosine of 2 alpha. So it's the same as we were having with 4x. Now we have 2 alpha. That means things are happening faster, twice as fast. So the normal cosine would have a period of 2 pi, and the cosine squared, which can be written as a half minus a half cosine of 2x, right? If you, plus a half plus a half of 2x, my bad. Here is the statement, has a period of, so t star, let's call it here as well, just a half of it, which is pi. All right, so far so good. Now, let us see what will happen if we have, for example, f of x being equal to the sine of square root of x. All right, is that periodic? So the answer is no, and we can show it with two, just let's say we just maybe show it with one advanced computation which needs derivation. Okay, so if the function is periodic, what it means is actually that f of x plus t, where t is a period, is equal to f of x. So actually we can skip the period. That makes sense. Now let's see if the function is periodic, what could we say about its derivative at x plus t? Well, basically that would be limit h towards 0, right? And then what we're having is, well, is f of x plus t plus some h minus f of x plus t divided over h, right? So the function itself is periodic, so we can kick t, capital T, out of the computation, which means we are having, I couldn't have done it here basically because I do not know the period connection to the derivative yet. but I do know it for the function. That's why I'm kicking it out. So I'm having x plus h minus x dividing over h, and well, that's the derivative of x, which means if what we proved is if the function is periodic, it also has periodic derivative. That's nice, because if we are computing now derivative of sine of square root, well, sine is cosine, we know that, square root of x times 1 divided over 2 square of x. And okay, for the sake of argument, I could take absolute value here. I'm not taking it. Let's say x are only such values. All right, everything is fine. But if, okay, now have a look at this one. If it's periodic, it must be happening over and over again, right? The same way, the same figure, the same shape. But you see here, if we compute a limit x towards infinity of f prime of x, well, the square root of x is going to be huge, and the cosine is never going further than 1 as an absolute value. So that means that the numerator is bounded by 1, and the denominator is unbounded, and it goes to infinity. So the value is becoming 0, which means this can never be periodic. And that means, through the proof we've done previously, that our function sine of square root of x is not periodic. So I've done also some theory behind it, but I think it's nice. If you're looking for knowledge, you'll find some more here, not only computation of given exercises. Okay, let's do one more example. Let's say we have f of x equal to, let's say, well, a times cosine of alpha x plus b times sine of alpha x. What could we do here? Well, now we have a combination. If it would be like only cosine and only sine, and we could maybe somehow do additional theorems or something, but they have the same lambda here. I said alpha. Did I say alpha? Sorry, my bad. Lambda. And that means the period normally for cosine and for sine for both of them would be 2 pi, but it's not. We are having lambda here and we're having lambda there. So the period here, t star, is becoming 2 pi divided over lambda, all right? Because we're exactly at this point, we're going to get the correct, like think about 2 pi and 2x. Okay, cosine of 2x, like we were having previously. We're dividing by this number, so we're dividing by lambda here, lambda, my bad. And well, cosine and sine, they are shifted to considering each other, but they do repeat after 2 pi, so it works perfectly. That's the answer. All right, and let's give me the last one for today. Let's say we have f of x equal to the square root of sine of x, all right? Well, that's nice again. Now, two ways to see what's going on. First of all, the sine is periodic, 2 pi, but the sine is going into minus negative values, minus area, where we got trouble. So the answer is immediately no. Okay, the function isn't defined everywhere, so we just have to, I don't know, like if we do this, what's the graph? Well, the graph of the absolute value of sine would be what? We're going this way, then we are going to reflect it, so it goes like this, and so on, all right? So it has a small, even way smaller period that we were having previously, all right? But the square root out of the sine of x isn't periodic since it's not everywhere defined, all right? That's the story. And the problem that we have is the definition must be fulfilled for every value. So if you have problems with domain, things can go bad, right? But let us forget about the problems with domain. Let us really assume we are only considering nice values that are positive, and for negative values we're taking absolute value, whatever. What can we see here immediately? Well, we can see that if we are considering f of x plus 2 pi, we are having square root out of sine of x plus 2 pi. And if the sine of x is given, the sine of x plus 2 pi is given as well, because sine is a periodic function. So we're going to get sine of x, which is a square root, which is just f of x, right? So we can go a bit further even, and we can prove if f is periodic, then that means that we are having a g of x, which is given as a square root out of f, and is going to be periodic as well. So once again, if you don't care about, or like skip the problems with domains like we've seen with the square root out of sine, all right? So it is periodic, but only for the areas where the function is defined, all right? So, and the period would be 2 pi as well, by the way, right? So if we're talking about this function, period t star is 2 pi, but let's say everywhere where everywhere if f of x is defined. Okay, so what can we say here if we're talking about g? Well, you see, if we have a period of t, what would we have? Well, the thing is, g is equal to, let's say we have f of x here, and it would be a square root out of f of x plus t, and you see it would be the same as square root out of f of x itself, because this is a periodic function. So g is also periodic, and it's having the same period. So g is also periodic. All right, thanks for watching. All the best. See you guys in the next video.